Welcome to another demo here at the Middleware 2020 conference named Hierarchical Topic Aggregation for Geospatial Applications through Processing Extension in Message Brokers. My name is Josef Spillner from Zurich University of Applied Sciences, where we look into creating distributed applications and services. In those systems, it is possible to define hierarchical topics. Let's take the example of Delft, the conference location, if it would not happen online. Delft is part of the province of South Holland, which is part of the Netherlands. So as a user, as a consumer of potential messages sent to a channel referring to Delft, I could simply subscribe to the topic hierarchy nl.zh.delft. I can also subscribe to nl.asterisk as a placeholder for all the messages appearing under the Netherlands channel. Now this is, however, delivering list semantics and not full tree semantics. Instead of really subscribing to the whole hierarchy at once, I am effectively subscribing to a list of channels which is known to be under the Netherlands. So instead, we would like to see real hierarchical messages, which is, however, not supported by any of the existing message brokers. So that if we would publish, for example, to the Delft channel, all of the subscribers to any of the Netherlands hierarchies would receive the message. And we would furthermore have the ability to not just propagate the message this way, but also intercept it and process it. For example, perform aggregation on the values that are submitted. How would we be able to achieve that? We can, of course, already achieve that with existing message brokers by adding a specific client, which you see in the lower left corner, a subscriber client that takes messages submitted to the Delft channel by subscribing to that channel, resubmitting the messages, potentially aggregating or otherwise processing them in between to the Netherlands channel. It would be, however, much more useful to have that functionality within a broker for several reasons. As you can see on the right side, we would have a similar functionality within the message broker, which allows us to spare one additional component in the distributed system. So to summarize and to complement, why would we be able to do that? First of all, we want to express arbitrary hierarchies. For example, we may not want to propagate our messages along a full tree, but rather along a partial tree based on certain conditions, constraints that we can only evaluate at runtime. May also want to propagate in hierarchies that do not have a typical tree structure. So going beyond tree structure, we may want to address graph models or any other arbitrary connections between potential channel topics. Further, we want the ability to aggregate on the way while the message is in transit. We may want to replace the message or complement it with additional information. This is very useful if you think about IoT integration, to have counters that count the amount of messages that have already passed by, or average calculation to have a gliding average over the recent messages. Furthermore, we want to spare the additional component. We have to reconsider that a message broker is already an additional component in a distributed system, and we would like to keep the maintenance effort down as much as possible. Finally, we would like to achieve more capable middleware systems that would by themselves already ship with domain-specific models, for example, existing hierarchy models. As you can see in the figure below, we often have changes to hierarchies. If we talk about geospatial and geographic context in general. We see that countries are essentially like files. They can be split, they can be joined, they can be renamed, and this is happening relatively often, so that we would like to consolidate the knowledge about those hierarchies in the broker rather than having to update, having to modify all the participants, all the publishers and subscribers in such a system. Generally, this is aligned with the trend towards more change-aware systems, smarter systems that come with their own knowledge bases, and also with the trend to deliver such functionality as a service on demand without having to engineer all the details manually. In order to implement such a functionality, we would need to gain support in message brokers. Traditional message brokers are not extensible. They work as monoliths. They process messages as they come and have a fixed processing model for them. Recent message brokers such as Pulsar have the ability to deploy functions. This is a concept known from function as a service, from serverless computing, which is very popular among software engineers and where there is a broad existing workforce of engineers that are able to bring such functions into the message broker, depending on the type of connectivity. Pulsar is offering a multiple input but single output model where we can connect to multiple topics upon deployment of our function, and it can process messages and send the results to an output topic or suppress the topic um, by not delivering the message any further. It is, however, also possible to deploy several instances of the function and therefore achieve also multiple output and therefore a true multiple input, multiple output model. All of the connections are specified at deployment time, and by filtering at runtime, we can suppress messages and therefore address only a subset of the output topics so that we are highly flexible in terms of where do we listen for new messages and where do we propagate aggregated messages afterwards. There are a number of use cases for such systems. In this talk, in this demo, we will focus mostly on geospatial hierarchies that are applicable especially to scenarios in smart cities and regions, as well as autonomous and digital mobility. We can also think of other hierarchies where this system would be beneficial, such as temporal hierarchies. If we think about reporting periods, we are reporting about certain metrics after collecting and aggregating them in different time periods. Such systems could essentially be integrated with time series databases. Similarly, we can think of organizational hierarchies as shown in the picture before. In businesses, it is quite common that people join and leave. There's a certain fluctuation, and we always want to address certain hierarchical levels, such as a team or department level, that allows for integrating with directory services. There may be further use cases when we go beyond the hierarchies, such as taxonomies and ontologies of subjects. For instance, we may want to address all subjects fulfilling a certain condition, and by evaluating the conditions at runtime and filtering the available subjects at runtime, we are able to do so using the proposed architecture. In detail, the geospatial hierarchies allow for three different directions of propagation. If we look at a country, as it is shown here, we have the ability for down propagation from the country level to the province or district level, to the municipal level, and further down. We have the inverse direction, upwards propagation from a city to a region and then to the country. And we have a sideward propagation, which is mostly of interest for any events which have a physical proximity effect, such as a contamination or a fire, which is reported and all neighboring regions are immediately informed. Within the proposed architecture, this is implemented as a multi-level propagation and aggregation workflow. As you see on the right side, we have a producer which produces an event, publishes the event to the level 2. The event is propagated to level 1 and further to level 0. An aggregation is being done. For instance, that event is added up to an existing number or variable. The result is then down propagated to the first and second level, and the consumer subscribing to the second level is essentially receiving the updated value. We can also visualize that as is shown in the picture below. We send a message to a certain city or municipal region, and we receive the event at a higher level, in this case, a cantonal level in the country of Switzerland. In order to facilitate that, we need to bring domain-specific knowledge about geospatial indexing systems into the broker. The broker needs to know what are the hierarchies, how are certain geographical positions and names related. A common standard in Europe, for example, is the NUTS system, which has several levels from the supranational to the national and subnational levels, which is often used for statistical reporting as, for example, the gross annual earnings in this figure. NUTS goes down to the local administrative units. However, it does not go down to lower levels such as streets or individual addresses or even individual point coordinates that we may need for certain use cases such as smart cities. Alternative geospatial indexing systems exist. On the left side, you see a mathematical system called a geohash, which is based on Z-order indexing. Any region in the world defined by a rectangle is covering at the maximum 4 geohash regions, and therefore any region can be specified by 1 hash, 2 hashes, or 4 hashes. In the geohash system, the length of the hashes is increasing with the level of precision that we need on a map. On the right side, you see H3, which is another indexing system accounting for differences in density of the population. This is coming from Uber engineering, where this is used for navigating passengers that use the mobility service. Let us start the demo by cloning the code repository of the HDA broker and running it in a local mode. Local mode means that it is simulating a message broker. It does not actually connect to a message broker, and therefore all the message transmission is working without any restrictions, as we have a true multiple input, multiple output way of conveying messages. HDA broker is loading 4 geospatial indexing systems with various numbers of entries depending on the level of details. One of them, geohash, is built in and can have an arbitrary depth and therefore an arbitrary precision. And the others are loaded from data files, which makes the system extensible. We can simply add additional geospatial indexing systems to the system. The HDA broker offers an interactive menu where we can subscribe to existing topics, where we can publish to topics, where the topics are also created in case they do not yet exist. We can list the topics, and of course we can try to check for new messages on any channels we subscribe to. In case it runs in simulation, this is a full application. In case it runs connected to a message broker, this application only acts as a client. We start with listing the available topics, and we see a number of top-level topics from GeoHash. Those are the single letters and numbers. We see names of cantons from Switzerland. This is coming from a Swiss-specific geospatial indexing system. We see names of countries. This is coming from NUTS. And we will see another indexing system called H3, which is the one with non-uniform sizes of regions. We can further drill down by going into each of those regions. So those are the individual regions defined by H3. We can also go into countries, drilling down in the NUTS system, and then we can start publishing. In case we publish to a name which is ambiguous or which is not fully qualified, there's a smart way of finding out which topic is actually meant. So if we just publish to France, we achieve the entire name of France. If we publish to Paris, this is automatically resolved as it is not a top-level domain to the city of Paris within the region Ile-de-France within France. Let us now see what happens if we subscribe to the province of South Holland. We see there is the implication of up and down propagation. We would have down propagation from superior structures such as the country, and up propagation from subordinate structures such as the individual municipalities. Now, if we publish a message to Delft, for example, we see that Delft is smartly resolved to the fully qualified name, Delft and Westland. The topic is published, and due to the propagation rule, the province of South Holland, since we subscribe to it, receives the event as we have fulfilled this inclusion rule. Now, as opposed to simulating all the connections in memory, we connect to the pulsar broker by launching first the Dockerized version of pulsar, into which HDA broker will automatically deploy the aggregation and propagation functions depending on our publish subscribe configuration. We start the broker. We see that it connects to pulsar, and we subscribe to Paris, for example. We see that the propagation function has been deployed, including all of the down propagation rules that were identified. And now we publish an event to France. We see that the event was successfully propagated. Afterwards, we manually check the message broker for new events, and we see that the event was received on the Paris topic, despite the fact that we were subscribing to the topic of France.